Good morning. Welcome to Krishna's classroom. Last time we stated the theorem that for a complex measure, the total measure or the total what you call the mod mu is countably is in fact the total variation of mu. Okay, the total variation of mu is a real measure. That's what we are up to, and we observe that this is total variation of mu of x is finite, and we were trying to prove this result. And in fact, I just outlined the various steps of the proof, and in this context we also proved one of the general results on complex numbers, and we will just briefly recall because we need it for our purpose. Okay, the lemma that we have proved was this. This we are going to use in the proof of the theorem. Are complex numbers then there is a subset S of the index set index set 1 to n, for which summation of belonging to the index set of zk is greater than or equal to 1 upon pi summation of k equal to now this is a very general result which we have proved already, and we shall require to use this at some stage or other. So I'll just put this star. Now we go to the main theorem that we want to prove. Mu is a complex measure on x, then the total variation of mu over x is finite. It's a very important result. Okay, let me just denote this by. Let us prove this result. Now I gave the steps of this proof in my last lecture, but let us now give the details. See, the art of proving this is through reductio absurdum. So what we do is, we note that there is some set. Okay, so if E is any set for which, so what we prove is this. M such that equal to infinity, then we can split E into the disjoint union of where M and A empty such that greater than 1 and infinity. So we prove this result first, and that is where we require the application of this particular lemma. Once you have this, what happens is, see, we start with x. Now what we do is we split this into two sets, A1 and B1. See, what you have is mu of, the total variation of equal to infinity. Therefore, our first split up will be greater than 1. So also mod A2 is greater than 1, and what we have is this infinity. So one of them has certainly this property, because the whole thing has this property. Okay, because you see that these are measurable sets and they add up. So this is what you have. Now what one does, so this is the one for which it is infinity. So once again you split this into A2 and B2. Then this is B2. So B2 you have A3 and B3 having the same property and so on. So you get a countable collection constructed in this, or the existence of which follows from the analysis that we would have done in the beginning. Okay, once you have that, then you look at this one. You have, say, this is the argument, mu of equal to sigma AI. But what is the problem? The problem is this. See, this is what you obtain from here. But what happens is, mu AI has the property that mod mu is greater than 1. Therefore, for every I, therefore, mod mu, see, does not go to 0. Therefore, this is not converted. So that's the problem, and that is the contradiction that you get. So if you assume the total measure, sorry, the what you call the mod mu x is infinite, then you arrive at a contradiction. So that's what we try to prove. Okay. So let us now start working the proof. So this is what you call the total variation. Okay. Let us prove this result. So we give the details of the proof. Suppose total variation of mu over E is infinite. So for that, we prove the following. Now you see, put T equal to this definition, pi 1 plus on mu. That's the definition of T. Okay. Now you see that since this is infinity, we have see this is a complex number. So this is absolute value of that. So this is some real number that you have. Okay. So this is greater than T because the total variation of E is assumed to be infinity. Therefore, this is certainly greater than a particular T that we have assumed. So we will call this 2. Okay. Since is greater than T, there exists a partition E such that let me take out this. Okay. Such that I will continue there. One to n greater than T. Why it is so? This is because now you see that how is this defined? This is defined, see, this is actually the supremum of sigma of this over all possible partitions of this. Okay, so we have this particular result following from the supremum of this sum that comes from that. Okay, right? The actual value of this would be something between t and this one. Okay, so that's what we are. That's why we are able to assert that there exists a partition ei of E such that this is true. Okay, so that comes from the supremum definition. So it's a consequence of the supremum definition. For B. Okay, and properties of because we are using the supremum. See, what we do is, we have this particular thing defined as supremum over all possible partitions of the sum of this kind. Okay, right? All possible sums of this kind. Okay, therefore, this is greater than t. That's what we want to. So you have this one greater than t. So the supremum is somewhere between. See, this is t and somewhere here. So we don't know. Okay, right? Therefore, we have okay. This is infinity. So therefore, what you have is there is some finite collection of ei partition of E such that this is greater than t. Otherwise, it won't go there. Right. Suppose there exists no such ei, and this won't be true. Okay, so this is very simple to see. Right. Now let us use the previous lemma now. Now, by the previous lemma, on complex numbers, setting zi equal to, zi is a complex number which is equal to mu of ei, we conclude that there exists a set A, there exists a set A contained in E En, sum of the sets E1, E2, En for which mu A, absolute value of this, is greater than T by pi, which is greater than. Now A is, of course, right? This is how you take A. Now this is contained in E. And for this one, if we take mu of Ek, then use the following theorem. What is the theorem that we have to use? Zk. So we use this result with Zi replaced by mu Ei. So we can actually work it out. If you work it out, then this is what you end up with. Okay. So then you get mu of A, that is modulus of mu of A, is greater than or equal to, this is of course the, how is A defined? Somewhere we have defined A. Yeah. A is a union of sum of the sets E1, E2, En, and that is the one that we have this. Okay. So for which you get this, get the result, and you have already defined T to be equal to pi times 1 plus mod mu E. Okay. So mod mu E is less than or equal to sigma mu Ei. Okay. So that part we have, and then pi is there. Now you see you see that this is by the result that we have, you get 1 upon pi, and use this result that this involves a factor of pi, and then work it out, you get the required result. So that's not difficult. I mean, that I leave it to you to just convince yourself that it is true. Okay. That is the place where the lemma is applied. Now it is simple. And this is greater than 1. So we have this as 3. So we have mu of A is that's something that you get. And what happens to this? Okay. So set B equal to E minus A. And A is a subset of E. Therefore, you take this, then we have mod mu B equal to because of additivity of mu, and you have B E equal to A union B minus A. Oh, sorry. A union B. E equal to, this is what we are using. Okay, therefore you get mu B is equal to mu of, what is it, E minus A, that you get, and that because mu is additive, you get this result. Okay, so this is greater than or equal to, this is just the property of complex numbers. That's very simple. Okay, and this is greater than t by pi minus what mean. Okay, and this, of course, by definition, this is equal to 1, because we have earlier set the definition of t in this way. The definition of t is pi so use this, therefore you get this result. Okay, and this is an important result. So you have this result, as well as earlier we have mod mu A is greater than 1. In fact, we also have infinity. The total variation of mu over B is infinity. So this result we obtain. Okay. Now what do you do? Thus, this is equal to, therefore we can split E into disjoint union of sets A and B such that and infinity. This is what we have proved. Now we shall use this. It is quite simple. So our starting point is x, for which so this is what we are given. Now what you have? Now, assumption that the total variation of mu infinity. We apply this result. If you have E for which the total variation of E is infinite, we can split it into the union of A and B. So we shall do this with X. Okay. Split X that is X equal to a disjoint union of this such that greater than 1 and infinity. So now that's the starting point. Now what you can do? We can do the same thing on B1. Okay, so this is the situation. This is X. X is now B1. So you have mu infinity. So we can do the same thing on this. So we can have A2 and B2. Okay. You know that such a splitting exists. Okay. Such that so that is possible. Now continue this process. Continue this process with BI. Once you obtain BI, you continue this process. Okay. empty, and mu of ai plus 1, natural value of that is greater than 1, and infinity. Okay, so this is the process that we adopt. So you can keep on doing it, and clearly a countably infinite collection ai with greater than 1 for every I. This is something that you obtain. Okay, what more? Now the countable additivity mu is countably infinity. But what you have, see, mod mu ai is greater than 1, mu ai does not go to 0 as I tends to infinity, since I. So what happens? The series therefore the series does not converge. This is a contradiction. Because what we have assumed is mu is a measure. Okay, mu is a complex measure. Therefore, if you have countable union like this, then this 4 should be true. Okay. So that is a contradiction. That doesn't happen. And the original assumption that that is the total measure or the total variation of mu over x is right. This is the conclusion. So this completes the proof of it's an important example in the sense that we have, unlike the non-negative measure that we defined, this is a property that, okay, for a usual real measure that we have been working with, real positive measure that we were working with, this result is not true, not necessarily true. It could be the whole of should be equal to 4. So you take the Lebesgue measure. You take the Lebesgue measure, you see that the Lebesgue measure of the whole real line is suddenly infinity. Okay, right? So when you come to complex measures, this is one of the substantial or major differences that you encounter. Okay, so I think I'll stop here today. Very short lecture, and from next lecture onwards we will look at the whole class of complex measures and then look at the structure that we just got. Thank you very much.